This is the fourth video for the 9.2 19.1 lecture series. This is going to be HL material looking at electrolytic cells with aqueous solutions. So we're going to be looking at the electrolysis of aqueous solutions. And because it's an aqueous solution, we're going to be including ions of both water, because as we saw from topic 8, water has the ability to dissociate into its ions. Albeit it's very small amount, it can still be there are still water or ions of water in that solution. And of course the ionic compound, because ionic compounds dissociate completely in water, therefore are represented in their ion forms. This means when you're going through the process of electrolysis, there will be selective discharge at the electrodes. So as we saw with the molten salts, your positive ion goes to your cathode, your negative ion goes to your anode. Well, now we're going to have two ions, one from water and one from your salt, that are going to be going to either electrode, and now we have to determine which one's going to be discharged. So if we look at water and just know and understand how water interacts at each of the electrodes, will help us to determine what's going to happen when we introduce a salt. So at the cathode, water has the capability to accept two electrons. And by doing this, it's going to release hydrogen gas. And then OH ions are going to remain in the solution. Which means, if you think about it, you could look at the pH. And that's going to increase the pH at the cathode electrode. At the anode, water has the capability of going through oxidation, therefore giving up electrons. When it does this, it releases oxygen gas. And if you notice, you have H plus being left behind, therefore decreasing the pH at that electrode. So now let's add in a salt. Okay, so once we add in that salt, and so we're just representing a generic salt by M plus, so your metal, and then your anion, right? And so that means at the anode, either your anion, so your negative ion, or water could be oxidized, and it all depends on the E theta value that you find in table 24. At the cathode, your metal or your M plus or your cation or water can be reduced, and again it all depends on that E theta value and determining which one's going to be selectively discharged. So which one's going to be, and how do we know? It is determined by the relative E theta value of the ions, the relative concentration of ions in the electrolyte, and the nature of the electrodes. All right, so we are going to visit each of these individually with their separate examples. So here, and so we're going to see those as we move forward when each of those would come into play. First, we're going to look at the electrolysis of water. So because the ionization of pure water is low, 1.0 times 10 to the negative 14, we must add ions, usually of another salt, to increase the conductivity of water. The ions, however, that we must choose must not interfere with the ions of water in order to work. And the whole point of splitting up water is to create hydrogen gas and oxygen gas. And so this is where hydrogen fuel cells come from, but it takes a lot of electricity, which is why they're trying to look at photovoltaic cells providing the energy to split water to get hydrogen gas and then use hydrogen gas fueled base fuel, which is a pretty cool idea. All right, so we already saw previously that we know that water can ionize. So we need to add a salt to help increase or further push water into its ionization. We are going to add NaOH to water. And we know when NaOH goes into water, it separates out into sodium ions and hydroxide ions. All right? So sodium, being a positive ion, a cation, is going to go to the cathode. Hydroxide is a negative ion, an anion, and it's going to go to the anode. All right, so there's a reason why we can use sodium hydroxide to help push the electrolysis of water, and you're going to see that. So at the cathode, what is going on? So we know sodium is going to go to the cathode to be reduced, which means it's going to gain an electron to become pure sodium. In order to do that, it has an E theta value of negative 2.71 volts. We also know, as we saw previously, water can also go to the cathode and it can accept electrons. And when it does this, it's going to release hydrogen gas and 2 hydroxide ions. Its E theta value is negative 0.83 volts. Because it has a higher positive value, it's less reactive, so therefore sodium wants to stay in ion form more than water. So water is going to be reduced at the cathode. At the anode, all right, so it doesn't actually really matter, but hydroxide can go to the anode, and it's going to make water, oxygen, and 4 electrons. Water also has the capability of going to the anode, and it's going to release hydrogen ions, oxygen, and 4 electrons. So at this point, if we look at their E theta values, the E theta value of just hydroxide is 0.40 volts. The E theta value of water is positive 1.23 volts. Now, it actually does not matter because if you look at the products, O2 and 4 electrons, same products for either one. So technically both will get oxidized at the anode. But for the sakes of knowing how to read the E theta values, because we're being oxidized, the lower positive number is the value in which we choose for oxidation. So now that we know which ones are going through our redox reactions, I'm going to quickly just circle them. Okay, so now that we understand which reactions are going through the redox reactions at each of the electrodes, we can write an overall balanced equation. So if we look at these and combine them, okay, so I'm going to put 4 waters plus 4 electrons gives us 2 hydrogens and 4 hydroxides. And then I'm going to take 4 hydroxides, and that's going to release 2 waters, oxygen, and 4 electrons. So the reason I had to multiply that cathode reaction by 2 is so that the number of electrons are equal and we can cross those electrons out, which then will allow us to write our full reaction, right? So combine the two and we can also reduce our waters. Here we go. We get 2 waters, and when those 2 waters split, we get 2 hydrogens and an oxygen being released. And so a lot of times they'll just say, hey, here's electrolysis of water, it's great, here's our reaction, very simple, but as you can see, the backstory to figure out how this process occurs is a lot more detailed. So the sodium is present to push further hydrolysis of water so that at the cathode, water can be reduced. Also, sodium pushes water to go into ion forms, allowing water to make hydroxide ions, including the hydroxide ions that were part of NaOH, allowing for a lot more of the hydroxide ions to be reduced at the anode. And lastly, of course, you're going to be asked, what can we observe? So we're going to see a colorless gas at each electrode, one for hydrogen, one for oxygen, because hydrogen is being produced at the cathode and oxygen is being produced at the anode. You're going to see their production in a 2-to-1 ratio. Because we have 2 hydrogens to 1 oxygen, we should see twice as much hydrogen being produced. As discussed previously, the pH at the anode is going to decrease because you are discharging the OH, which means your H plus is left behind, decreasing your pH. The pH at the cathode increases because we are discharging the H plus, leaving behind OH minus, therefore increasing your pH. And so this is what an example of going through the process for electrolysis of aqueous solutions. And this is just the setup of what what it would look like for an electrolysis, especially when we're creating some gases. So if you know what your products are and what's going to get discharged, you know how you need to set up your electrolytic cell. So this is a little bit different than I had shown you in the previous video. Because we're collecting hydrogen and we're collecting oxygen, we need to have a vessel in which to collect those gases. So you can see we have our big electrolytic cell. Then in the electrolytic cell, we're going to have some kind of tubing, test tube, something to collect the gases. And so we have our external wire being submerged. You have your inert electrodes like platinum. And then that allows, once we start to get the electricity to flow through the solution, allows for the production of your hydrogen and oxygen gas. And you can see that it is in a 2-to-1 ratio. Now we're going to be looking at the electrolysis of sodium chloride. And so this example is for the second one of determining on the concentration of ions present, because depending on the concentration of ions can determine which ion is going to get discharged. So when we go through the electrolysis of sodium chloride, also known as brine, brine is a very heavily concentrated salt solution. We are going to produce H2, Cl2, and NaOH, which are all commercially important compounds, and so this process actually occurs quite often. So what ions are present in this solution? We have NaCl, and it's going to be in an aqueous solution. And as we know, it's going to split up into Na ions and Cl ions. NaCl positive, it's a cation, so it's going to go to the cathode. Cl is an anion, therefore it's going to go to the anode. So now what we're going to be looking at is what's happening at the cathode. All right, now what we have present at the cathode, if you go back and you remember from the previous example, we have Na plus, right? And we have, which has a E theta value of negative 2.71. We also have water, right? And that has an opportunity to get discharged as well, and that has an E theta value of negative 0.83. So this is the same exact example as in electrolysis of water. Water is going to be discharged at the cathode. The anode is where it's different. So at the anode, two things can happen. If we have a low chlorine ion concentration in our brine solution, OH minus is going to be discharged. So that means, just like in the previous example, we have 4 OH ions that are being provided from water, and that is going to produce 2 waters, oxygen, and 4 electrons. And as we know, that had the E theta value of positive 1.23 volts. Because chlorine is much higher on the list, if you look back at your reactivity series on table 24. Now, what we actually care about, because if we have low chlorine ion concentration, we're just going through the electrolysis of water. It's no different than the previous example. So what we care about in this example is a high chlorine concentration, which is why this concentration of high chlorine, it's usually a 25% by mass a sodium chloride solution. So it's really a hefty solution. Okay, so now because chlorine is overwhelming majority of ions present at the anode, it is going to essentially be discharged over the hydroxide ions. You don't need to know the complex science behind why chlorine is, you just need to know that it does happen. And so when this happens, you get Cl2 gas and 2 electrons. And this has an E theta value of positive 1.36 volts. And you can see that they're relatively close. And so typically you can understand why hydroxide would be discharged first, because it has a lower positive value. But again, due to the overwhelming amount of chlorine present, 25% by mass gives us enough to have chlorine overwhelm that of hydroxide. So now we can go through and we can put together the full reaction of looking at the chlorine discharge. So we're going to look at chlorine discharge and we're going to be looking at water discharge. So that means we have 2 waters plus 2 electrons, gives us H2 gas, which is one of the products we want out of this, and 2 hydroxide ions. We also have our sodium chloride, in which case we're going to get a chlorine plus 2 sodium ions plus 2 electrons. Our electrons already match, and it does not matter if you do just Cl minus or actually the salt being present, but the salt is part of the solution, which is why we're writing it, and it is partaking in the solution. So when we do this and we combine them, we have 2 waters that react with 2 sodium chlorides. And when they go through this process, we're going to release hydrogen gas, chlorine gas, and if you look at what's left behind, we have 2 hydroxide ions and 2 sodium ions, which make 2 NaOH compounds. And so now we can get 3 very important products that are used in industry worldwide. What do we observe? Well, we're going to see a colorless gas at each electrode, hydrogen and chlorine. Chlorine gives off a very strong chlorine distinct smell, and it has a bleaching effect. And the pH at the cathode is going to increase because we're discharging the H2, right? Which means OH minuses are being left behind, therefore increasing the pH. And so that is the example of how concentration can affect the discharge within an electrolytic cell. The last example is we're going to be looking at copper sulfate. And with copper sulfate, what we're going to be looking at is the type of electrode, like what is it made up of in the solution, and how that would affect what gets discharged. So in a copper sulfate solution, we are going to have copper, which is Cu2+, and sulfate, SO4 2-. Copper is going to go to your cathode. Sulfate is going to go to your anode. So we're going to look at our first example if we're using an inert electrode like carbon or platinum. So what's happening at the cathode? So here we have our Cu2+. So it's going to be reduced by accepting 2 electrons to make pure copper. That has an E theta value of positive 0.34 volts. Water is also present, so as we know, water has the capability of being reduced, and it produces H2 and OH minus. This has an E theta value of negative 0.83 volts. So as we know, which one is going to get reduced is going to be the one that has the higher positive value. And so that means our copper is going to be reduced. It's going to be selectively discharged. At the anode, water is going to be the one being discharged. So water is going to interact with the inert electrode, giving off 4 hydrogens, oxygen, and 2 electrons. The E theta value is positive 1.23 volts. Sulfate, and the reason why sulfate would not be reduced is if it was going to be reduced, it would actually create a strong acid that would then redissociate back into solution. So sulfate is actually very hard to pull out of solution. We have to do some other things to get that to work. So here's water is going to be oxidized. So what that overall equation looks like. So we're going to be using water, and we're going to be using copper. Okay, so now I'm going to rewrite these. So we have copper sulfate, and we know that copper sulfate is going to be releasing 2 electrons, and we care about that copper, right? And then we have our water, and it's going to be giving off 4 H pluses and O2. and 2 electrons. So they're already balanced, so we can cross those electrons out. Nothing else can be crossed out. And so now we can go through and we can write our full equation. So copper sulfate reacts with water to produce pure copper, oxygen gas, and here you go. We are going to be going through and creating sulfuric acid, right? And that is why I told you that this is also going to strongly dissociate, as we know, so it is going to dissociate into our 4+ ions and our 2 sulfate ions. Either way works. You can either write it as the compound or as themselves as an ion. That helps you remember that sulfuric acid is a strong acid. Write them in their dissociated form. It doesn't really matter. So what we're going to see is we're going to see pink-brown color at the cathode due to the fact that copper is being precipitated out. A colorless gas at the anode because oxygen is being released. And you're going to see the pH at the anode decrease because the hydroxide is the one being oxidized, therefore leaving H pluses behind. And we're going to see a loss of blue color because copper ions are blue in solution, but as we lose those copper ions, it loses that color blue and eventually would go colorless. So that is what happens when you're using a carbon or an inert electrode. So what happens when you use copper electrodes? Okay, so if we're going to be using copper electrodes, then I'm just going to rewrite the ions so you remember. Okay, so if we're going to be using copper electrodes at the cathode, we're going to see the same as above, where copper is going to be selectively just discharged over water due to its E theta value. The anode, however, what you're going to see happen is the copper electrode is oxidized. The electrode itself, supplying the electrons. This is causing the dissolving of that electrode into Cu2+ ions. So really what's happening at the anode is neither water nor sulfate's actually going to be going through oxidation. It's the electrode itself going through oxidation. So that copper of the electrode is just going to re-release copper ions and electrons. So there is actually no net-based equation because the copper ions that are being uptaken at the cathode are being resupplied at the anode. So there's no change. So what we're going to observe is a pink-brown color at the cathode due to copper being precipitated out and being reduced at the cathode. But at the anode, we're going to see the disintegration of our copper electrode because it's going to be the one being oxidized. We're going to see no pH change because nothing's being discharged at the anode. And there's going to be no change in blue color because the copper ions are just being resupplied. And so those are the 3 examples of electrolysis. So electrolysis of water, electrolysis of salt, and electrolysis of copper sulfate.